All right, good morning. My name is Fahad Vora, and I'm joined by Michael Baldwin, and we're going to present on motion tracking technologies. Just to give you an overview of the presentation, we're going to go briefly over the history, starting from rotoscopy to going into modern day applications in military, gaming, etc. And then we're going to go more in deep into the different methods of motion tracking, which can be camera-based or mechanical. So over here, you can see a picture of a rotoscope from the 1970s. An original motion capture film is projected onto a transparent glass panel mounted on an easel. And the artist basically traces the outline of the performer and converts that into animation to give the rendered animated characters a more human, fluid-like motion. Obviously, this was very cumbersome and very time-consuming, didn't last very long, but motion tracking has come a long way since then. Talking about the modern-day applications, we use VR headsets in military to train soldiers in combat training. Then we use motion tracking to track performance of athletes, and also sports companies use it to design better products, like Nike uses tracking data from athletes to design better shoes. It's used in motion capture, performance motion capture in films to give the animated characters a more human-like look, and also it's used when the possibility of using real animals is not feasible. Also in ubiquitous interactive gaming consoles like the Microsoft Kinect. Now I'm going to talk about optical methods that use cameras. So in any kind of input-output systems, you have a sensing component. And the sensing component over here is the CMOS sensor in your camera, which works basically on the principle of photoelectric effect. So you have light passing through RGB filters, the photons getting stored in semiconductor buckets. There's some analog to digital conversion going on, and the data is read pixel by pixel and converted to the image that you receive on the other side. So once you have the image, you can do a lot of stuff with it. For example, you can do thresholding to convert the image into binary. You can do histogram equalization to adjust the contrast of the image. But specific to motion tracking, I'm going to talk about the concept of using convolution masks to detect objects. So if you have an object placed against a background, you have a change in the light intensity from the object to the background, which can be picked up by the CMOS sensor using this convolution mask. So over here you see we have a gradient convolution mask, which if you apply to this pixel area, it will give you the offset of the light intensities from the object to the background. And that's how you detect edges of an object. Then you can use techniques such as blob analysis to identify connected edges, and you can basically come up with the bounds of the object. And you can do further analysis like figuring out the shape of the object. You can do infer the geometry, the geometric center, etc. So now that we've covered some of the basics, I'm going to delve straight into the marker-based motion capture. Over here, you can see a violinist performing with a bunch of markers on his body. These markers are coated with retroreflective material, and so it makes it easier for the software to identify the markers from the background using techniques I mentioned before. So you have a 2D image and you have a set of markers, but to get a realistic worldview, you need depth information, which is achieved by using stereo triangulation. So if you have two cameras placed at a known distance apart, and if you know the intrinsic properties of the cameras, like the focal length of the lens, and if you know the shift of the object in the two images you obtain from the cameras, it's using simple optics and geometry, it's easy to identify the depth. So using stereo triangulation, you basically create a point cloud, which is a 3D representation of the performer. So now that you have a point cloud, you run into the problem of temporal correspondence, which is how do you track the set of markers or the point cloud across frames or across time. This can be done using several techniques. One of them is the software comes up with a strength matrix that correlates the likelihood of one marker being in one frame to the same marker being in another frame. Um, and using that, you can track the set of markers across frames. So over here, you can see motions of crawling, bowing, jumping, tiptoeing, and the markers, trajectory of the markers that are tracked. Sounds simple enough, but then you run into the problem of occlusion, which is sometimes the markers can be hidden using, or markers can be hidden from the field of view of the camera, or the observer's body can obstruct the markers. Um, Several ways you can use to solve this problem is use a bunch of cameras and have the performer be always within the field of view of at least one camera to track all the markers. But that still doesn't solve the problem of the performer hiding the markers placed on its own body using its subparts. You can solve that using by placing markers strategically on the performer and making a kinematic model of the performer, of the motions of the performer, and you can predict where the missing markers can be. Now I'm going to talk about performance motion capture, which is used heavily in films. Nowadays, they can use anywhere from 30 to around 300 markers to capture intricate details of the performers, like facial expressions, for example. The precision can be pretty high. So for performance mocap, it can be sub-millimeters, or if you're using really commercial systems, it can be on the order of 15 micrometers. And you can use performance mocap to, so actors use this to play humans, they can play animals, they can play, just weird things. But the takeaway is that performance motion capture has its pros and cons. You can be really precise, but it's really limited by the setup time of applying different kinds of markers to or hundreds of markers to the performer's body, having a controlled space, having a bunch of expensive and heavy equipment that's really time consuming to set up. Now I'm going to talk about marker-less motion tracking, and specifically the Microsoft Kinect. So the Kinect uses structured light, so it projects a known pattern of IR dots onto the view space of the camera, which is picked up by another camera, and using stereo triangulation, it comes up with a depth map like we've seen from the previous slides. The interesting thing about the Kinect is that the next step is it uses randomized decision forest to identify pixels that may correspond to specific body parts. So the decision forest is an algorithm that can ask questions like, okay, is this pixel at this location offset from this pixel at another location by so much? If so, then this pixel most probably is a shoulder joint or a knee joint, for example. And then this is how the Kinect comes up with a skeleton of the gamer or the player or the person in view. And the interesting thing about Kinect is that even though it might look like it's tracking the motion of the performer or the player, it actually just renders the skeleton frame by frame over and over again. So it goes through the entire process frame by frame. So it doesn't actually track it, but recreates the skeleton over and over again. Just an honorable mention about a commercial system we might all be familiar with is the Hawkeye, commonly used in tennis and cricket. You have a set of 10 synchronized cameras placed around a tennis court or a cricket field, and each camera identifies pixels associated with the ball, and then the software comes up with the most statistically probable trajectory of the ball, and that's how it tracks the ball without using any markers.